Hello everyone, this is Sinan Ertemel. Welcome to my sixth lecture, which will be about Nash equilibrium. So far we talk about two different solution concepts, ranging from minimum axioms to more axioms. So the third equilibrium concept that I will introduce today is when the first two concepts are not giving me any outcome. So I am stuck according to sophisticated equilibrium concept. So I might find some dominated strategies, maybe I eliminate them, but still I don't get any single outcome. Or I might not find any dominated strategy at all. So I am stuck. I don't know how to proceed. Is there any reasonable way to predict the outcome of such games where there is no dominated strategy? And here the idea of John Nash, which coined this very important equilibrium concept, comes into play. And Nash's equilibrium concept based on the idea of the best responses. So in the equilibrium, all the players are playing the best responses according to the other players' equilibrium strategies. So what does a best response mean? The best response is the strategy that gives you the highest payoff. And you will find that for each and every other strategy for your opponent. And I'm going to illustrate that in different games. So the Nash equilibrium is based on the premise that each and every player is playing best response. So each and every player is maximizing her utility according to other players' other strategies. So this idea of the best response is very powerful for the motivation of the Nash equilibrium because it involves the self-enforcing property, which is there is no unilateral deviation for any player. So if you deviate from equilibrium strategy, you cannot be better off. There might be scenarios where players can move cooperatively to a different outcome, which we argued in Prisoner's Dilemma. That's not likely in a simultaneous game. Yet, if we consider deviations by one player only, unilateral deviation, Nash equilibrium dictates the fact that it is impossible for one individual player to get a higher payoff by deviating from Nash equilibrium strategy. And Nash equilibrium is very popular among social scientists because Nash himself proved in his 1951 paper for a finite game with finite strategies, Nash equilibrium always exists. Okay? But the other two concepts that we talk about, it based on the fact that there is a dominated strategy so that I can move forward. So it doesn't exist always. You have to have a dominated strategy in order to have either dominant or sophisticated equilibrium. However, Nash equilibrium, it always exists. But you have to remember that sometimes there is no Nash equilibrium in pure strategies, where player is taking one particular action. So there could be no pure strategy Nash equilibria. Existent property is based on the fact that people can choose mixed strategies. So they can play strategy A with some probability and strategy B with another probability. So by randomizing strategies, Nash equilibrium idea says that the equilibrium exists. So that's a very powerful property. On the other hand, in some games, we might have multiple Nash equilibria. That poses another problem. So the predictive power of standard game theory doesn't answer which Nash equilibrium emerges when we have multiple. So in that case, I am going to introduce other concepts such as the focal points that would tell us which equilibrium can be more compelling in some specific cases. So in order to illustrate Nash equilibrium, I would like to start with the game that we solved earlier via dominant strategy equilibrium, that is the prisoner's dilemma. So let's find the Nash equilibrium of the prisoner's dilemma again. So the idea was to find the best responses, and the Nash equilibrium outcome is the outcome where each player is playing best responses. So best responses coincide. So we need to find best responses, starting with the first player. And what's the best response if Bob confesses? Okay, so if Bob confesses, and has two options, confess or not. Confess gives -5, and not confess is gonna give -6. So the best response would be -5. So if Bob confesses, Anne would confess too. If Bob denies, okay, then if you confess, you will be free, 0. Otherwise, you will get -1. Confess brings a higher payoff. So confess is the best response. In order to illustrate the concept, I put underline to best response payoffs. Okay, so next I will find the best response for Bob. If Anne confesses, Bob would confess too by a similar argument. And if Anne denies, then the best response for Bob would be confess. And if you look at the intersection of the best responses where they coincide, where both payoffs have underscore, we see that it is confess, confess. Here we have also beliefs that are consistent. That's another motivation for the Nash equilibrium. Suppose Anne believes that Bob would confess, then Anne would confess. According to that belief, Anne's best response would be confess. And similarly, if Bob believes that Anne would confess, his best response would be confess. So we have beliefs, and each one of them is acting according to those beliefs, and the belief structure is consistent. So that's the Nash equilibrium. And remember the dominant strategy equilibrium, where we find whether a strategy is dominating every other strategy. And we saw that in prisoner's dilemma, for both Anne and Bob, confess is the dominant strategy. So if you find the dominant strategy equilibrium, then we get exactly the same outcome, confess and confess. Okay, let's move to the second equilibrium concept, which is sophisticated equilibrium, where we eliminate dominated strategies. Confess is dominant and deny is dominated. So if I eliminate deny for both players, I end up with confess and confess. So sophisticated equilibrium gives me the same outcome. So there is very important property, which is quite straightforward. If a game has a dominant strategy equilibrium, then that equilibrium outcome is also sophisticated equilibrium outcome. And when we have a sophisticated equilibrium, corresponding outcome is also Nash equilibrium outcome. So you see, going from the first to second and third, we are refining the equilibrium concept. Every dominant strategy equilibrium outcome is sophisticated equilibrium outcome, and every sophisticated equilibrium outcome is also Nash equilibrium outcome. So let me give a second example where dominant strategy equilibrium does not exist, and we are going to solve this game by finding best responses. So this is linear city model, which is also introduced by Harold Hotelling in 1929. Suppose there is a there's a beach which is 1 kilometer long, 1,000 meters, and there are 1,000 beach goers in each meter, so equally distributed. At 1 meter length, there is one person. And there are two ice cream vendors, Ann and Bob. They are selling identical ice cream with the same price. So my question is, where would Ann and Bob put their ice cream stand? At what location? Would there be on the opposite corners, like 0 and 1,000 meter, or somewhere in the middle, like to the left, to the right? Ann is at 250 meters and Bob is 750 meters. So what would be the answer? According to Nash equilibrium, which is each player is choosing best response. So let's start with this possible location. Would it be best response for either Ann or Bob? If you see Ann is closer to 0, say at the meter 250, and Bob is at 750. And I will argue that neither player plays the best response. Starting with Bob. Is Bob playing best response? So according to Ann's strategy, is he doing the best that he can? The answer is no. If I know Ann is at 250, I will be a little bit to the right of Ann, so that I can get all the consumers to the right, which is 750 people. And Ann would get only 250. So by moving to the right of Ann, just 1 inch to the right, I will get all the people between 250 and 1000, which is 750 people. So Bob is not playing the best response. Similarly, Ann. If Ann knows Bob will be at the other corner, like 750, Ann would do a little bit left to Bob, say 749, like 1 meter, 1 inch to the left. And in that case, Ann would get 750 consumer. She will sell exactly 750 ice creams. So neither player is playing best response. So this configuration is not Nash equilibrium. But I think you guessed the best response dynamics and where it's going to take us. So if you are to the left, like not in the center, the other person will be a little bit to your right. And then as a best response, you would be to his right. And so on. They will outright each other until they come to the middle, 500 meters. And there they will stop. Because if one player goes any further, he's gonna get less than half of the consumers. So they will be both in the middle and they will share the market equally. So that will be the Nash equilibrium outcome. And maybe this is not a good news for the consumers, right? Especially the ones who are in the very corners. They have to walk 500 meters in order to get one ice cream. So two ice cream vendors, ice cream is the same, the price is the same, and the location is the same. So we don't provide much diversity for the consumers. So in industrial organization, this outcome is called the minimum product differentiation. So we observe this sort of equilibrium in many different contexts. I mean, maybe not just physical location. If competition occurs to one spectrum, it can be taste of the ice cream, or it can be for another good, the color, the size. So we see that if there are two competitors, they will converge at the same point. But if there are more than two, you will see that three or more of them being in the center, will not be equilibrium. But for two sellers and with only one parameter where competition occurs, we end up with minimum product differentiation. And another application happens in political science. And this interpretation is called the median voter theorem. If we have two political parties or two presidential candidates, and if they are competing on one single characteristics, which would be, say, free healthcare, so these two political parties or presidents will end up at the choice of the median voter. Whatever the median outcome is, they will try to set their platform exactly at that location. And I would like to also argue about the optimality of equilibrium. It is not optimal because, as I said, the transportation cost is too high. People in either corners, they walk too much in order to get one ice cream, and they are sharing the market equally. So we could have another configuration where they are sharing the market equally, but the transportation is minimized, and that would be, and one of the sellers will be at 250 1/4 and the other 750 3/4. That's the social optimum in which the transportation cost is minimized. So that's the end of our lecture, and in the next lecture I will talk about another interesting game where we have multiple Nash equilibria. That's going to be game of chicken. See you all in the next lecture.